So welcome everybody, and I just want to say thank you for attending the last session of the last day. I appreciate all of you, attending. So let me get started with a quick introduction. So my name is Eriko Nurvitadi. I'm a co-founder and chief product officer for MangoBoost. I also run MangoBoost North America, and today I'll be co-presenting with my collaborator Craig Carlson here, who is a networking and storage architect from AMD. And today we'll be talking about accelerating GPU server access to network attached disaggregated storage using data processing unit. Okay, so here's the agenda, right? So first, I'll talk about the trends in AI and implications on storage systems. And then I'll hand it off to Craig, who'll talk about AMD GPU ecosystem for AI. And then I'll go over the opportunity for data processing units, the modified DPU, and then how it could help AI. And finally, we present concrete case study. This is on LM training on MI300 AMD GPU servers equipped with MangoBoost DPUs for storage acceleration with NVMe TCP. All right, so let's start with trends in AI. So I think this is not controversial. I hear a lot of people talking about this already. But AI has been very disruptive, right? And then, very notable example is the ChatGPT. One could say that it could be the first real killer app for AI, right? And as shown there in the figure, it not only cool technology, but it also got adopted, right? 100 million users in 2 months. So it's record-breaking at a time. So that's kind of how people got the real use and people paid real money for AI services. And similarly, there are many reports out there. One of the reports I just happened to highlight there is on the market size for AI, right? Now it's a quite big market, even 2024, already 15 billion, and then it projected to be 250 billion in 10 years or so. And more importantly, right, it's not like necessarily just a one app kind of thing. So after ChatGPT, there's so many other offerings. I'm not including everything here. But you see, as an example, video generation, right, AI capability. I've seen, people providing service for, music generation, image generation, multimodal stuff. There's so many offerings proliferating in the marketplace, and people are adopting and using it. So, it looks like it's going to continue to stay hot in the foreseeable future. So, very exciting time. And then there's many branches of AI, right? But for now, I think we're focusing on just what arguably the most popular one, which is a large language model. And here's just one picture to show kind of the trends. And there's multiple sources tracking the what's happening with LLMs. And this is a snapshot from June 2024, right? And then you can see a different circle that represent the size, of the model. But LLM these days, the biggest ones go over trillions of model, right? 1.5, 2 trillion, and so on. And more importantly, there's multiple of them available, right? And in the trillions. And not only that, there's also a family of these kind of models. Not only the super big one, trillions, and continue to grow, but also the extra large, which is hundreds of billions, to medium and small, which is tens of billions, to smaller models, which is a few billions. Right, so there's a variety of models available. It continues to proliferate. It moves fast, and it get bigger. But also the small, medium, and large is still continue to be used and then continue to be offered. So as systems people here, right, we ask ourselves, how to build efficient AI systems for LLM. Especially taking account that these model sizes continue to grow. So let's first look at the hardware trends, right? One of the observations I want to highlight here, and I think others have also mentioned things like this in other talks, is that AI systems increasingly more challenged by data-oriented tasks, right? There's a compute, and sort of roughly there's also data movement, data store, and all that. And one observation, right? There's multiple figures like this outside. I pick one example. I guess the legend is a bit small, but basically the x-axis is showing trends over the last 20 years or so. And then the y-axis is showing improvement over time. And then the gray line that's showing the compute, the amount of compute on chip, right? From flops to more recently is the tensor ops, right? Whatever variety of precision you have. But there's more and more compute, and more recently, obviously, AI compute put on chip. So it's a 60,000x improvement in the last 20 years, right? It moved very fast. And you can kind of also see, you look at all the chips you have these days, Obviously, GPU is very popular and has more and more tensor computation in it. But you can also see CPU now have tensor instruction, right? AMX, for example. It has a AI engine going to CPU client laptop, right? Even FPGA has a tensor DSP, has the AI engine as well. Your smartphone has a compute for AI. So compute is becoming more available in hardware and continue to grow fast. However, if you look at the trends in terms of off-chip memory, interconnect bandwidth, those are the other lines, blue and green, right? The improvement is much lower. One other way to look at this is in terms of the capacity, the GPU memory capacity available in the device, right? GPU has HBMs with high bandwidth, but the capacity itself, even though it's continuing to grow, but it's also not keeping up pace with the growth in the LLM size, right? So similar kind of the graph, right? X-axis is trends over time. And then there's two lines, again, don't worry about specific data point, but there's the green line that is showing the growth in the amount of capacity in GPU device memory. And then there is a red line that is showing the size of the LLM models, right? And as you can see, the red line surpasses and grows much quicker. So what does that mean, right? So it means that today, right, LLMs, a lot of them don't really fit in one GPU card anymore. If you just rely on the GPU memory, then it won't fit, right? Because just a much bigger model going on. So and then we attempt to estimate here the number of GPUs needed to fit an LLM model, right? And so we take for every year, X is again years, and the Y-axis is the number of GPUs. If we take state-of-the-art GPU and state-of-the-art LLM model for that year, we make some projection as to how many GPUs. As you can tell, number of GPUs needed just to fit the model in terms of the memory capacity. It takes more and more GPUs. So clearly, we would need to think about larger storage options, right? And so that brings me to the next point, right? So in the industry and then our technologists, right? People already been pushing in the recent years towards optimizing more AI storage systems, right? There is a software framework that's now being more and more optimized for AI for storage systems, as well as there's benchmarks tailored so that it can evaluate the AI storage subsystem. So I'm going to highlight, for example, the AI framework. A lot of the innovations that we've seen has been in terms of being able to spill the data out of GPU memory to use system memory as well as disk, right? So that going to other places where you get bigger capacity, obviously at the trade-off of bandwidth and latency, but smartly managing that. So I think there's already other talk that talks about the different options. I'm just going to highlight one here, which is Microsoft DeepSpeed. And this is very popular software, open source, ran by Microsoft, right? And again, this is the picture from their paper. Essentially, what they do is they're able to offload model states, right? And this could be not only the weights or the parameters, but gradients as well as the optimizer states, spill out of the GPU and then to CPU memory. They call it slow memory, CPU memory as well as SSDs. And then by doing this, right, even if you don't have enough GPU to fit the model into the memory capacity of GPU, you can still run it, and then depending on your configuration and how you tune it, you could also get quite good performance. At least try to maximize the GPU that you do have, right? And then even though the model go in and out of the GPU memory. And the next one I want to highlight is there's also benchmarks now that is targeted towards evaluating AI storage subsystem. One I particularly want to highlight is MLPerf storage, right? You might be familiar with MLPerf consortium, and traditionally what's the most popular is MLPerf inference, and training has been going for a while, right? Everybody kind of submit their latest numbers there. But more recently, there's also MLPerf storage. Some of you might already know this or might already participate, but those of you who haven't, I encourage this community to check out MLPerf storage. So we've been, MangoBoost, we've been participating since earlier this year. There's already one published results last year, and then the version 1.0 is actually, the deadline just passed. We submitted, and there's other submitters as well, and it's being reviewed. So the result is going to come out next week. And here, the setup is shown there on the figure. Essentially, the metric is really the throughput coming out of memory storage subsystem to feed the accelerators. And this is emulating modeling the case for training. So where the data set comes from disk, and then it's being fed to a number of GPUs, right, or AI accelerators. So what's interesting here is that the AI accelerators is, they don't require you to have the AI hardware in there, so because not everybody have many GPUs. So the GPU computation or AI computation is modeled using just sleeping, but there's a methodical approach to estimate that, and the MLPerf storage workload is capturing that kind of modeling. And then, but the storage subsystem using PyTorch going to access the disk, that's real, and that's measured throughput. And then the other metric is to show how many accelerators can be supported, because obviously the more throughput you have from your storage, the more accelerators you can support, right? So that's kind of MLPerf storage, and we actually have very good results. So if you're interested, check out next week. It should be a press release and all publication, and check out other results as well. And again, I encourage you guys to check out MLPerf storage. It is very relevant to this community. And there are also other benchmarks I'm not showing here. There's also spec storage, TPCX, AI, and so on and so forth that also, again, evaluate the storage subsystem, right? So again, this is very interesting for storage community because, in the previous case, MLPerf inference, for example, is not touching storage. MLPerf training, even though there is storage in there, but it's not isolated to know what is the metric for performance for storage, right? It's only end-to-end kind of thing. So it's very exciting. So next, in terms of systems and hardware, right, there's also an increasingly more need for disaggregated storage in these AI systems, right? Obviously, disaggregation and disaggregated storage is not necessarily a new concept, but it's even more important, I think, now that we're looking at the trends in AI. So this is obviously a very simplified cartoon, but you have a storage server on one side, right? You can have a lot of SSDs, and then you can pull the SSD and make it accessible through high-speed network. On the other side, you can have many GPU servers, right, that access the storage. And obviously for AI, some of the benefit would be, first is high throughput, right, and capacity. Right? Obviously, if you have multiple SSD in the box, so you have more capacity, but you also have throughput because multiple SSD bandwidth can be aggregated and then accessed through a super high-speed network, right? For example, 100 gig network link, you can put 3 or 4 SSD together, and you can saturate the 100 gig, assuming your network can keep up. And you can pull also multiple network ports together. And in this case, it's important for providing the data to the GPU server because we don't want the GPU to be idle, right? We want to max out the compute utilization of the GPU, and also for large model, AI states, right? We need the capacity as well. And in terms of disaggregation, obviously the known benefit is eliminating over-provisioning, right? We can flexibly configure and assign resources of storage to the right GPU server. And it's important because, as I mentioned, right, there's a variety of workloads. Even the model, there's a big model has multiple variation. Super big model has multiple variation. Some are smaller, a bit smaller, some a bit bigger. So you want to assign the right resources for these different instances. And on the GPU server side, right, this GPU server trend is toward more and more dense server. So you want to pack a lot of GPUs. You have to deal with thermal and all that stuff. So you ideally want to utilize the most of your PCIe slot, PCIe link that connect to your GPU, right? Because you want to make sure it's fully utilized, and you want to make sure it can get the data through, right? If you have one PCIe slot and you connecting it to GPU, if you have an SSD, one SSD may not be enough to saturate the bandwidth, right? But if you have a NIC instead, one NIC, you can have high-speed network, right, or one DPU in this case. And then you can basically group multiple, remote storage, right, resources to really saturate this. So each GPU get the most data from the available PCI link in this case. So that way, GPU can still be dense, and you don't have to put too many cards. Just put enough of this NIC to match the GPU link, right? NIC or DPU to match the GPU link. And this would help with the form factor and also improve the bandwidth utilization, as I mentioned. Okay, with that said, let me hand it off to Craig.
Thank you. Yeah. So I'm going to talk a little bit about the ecosystem that these guys have been using. AMD GPUs, if you're not already aware, come in 2 classes. You have the Radeon, which is your gaming GPUs that you can go out and buy and put in your gaming box and get good performance. And then you have your Instinct GPUs, which are the big guys. Those are the ones that are the data centers. And they're the ones that come with HBM memory and Infinity Fabric interconnect to connect the GPUs in a very high-speed interconnect. But you also have to have, when you have the hardware platforms, you also have the software platform as well to take advantage of it. And that's the ROCm development platform, which is something that AMD has developed open source, and it actually supports both types of GPUs, both the Instinct and Radeon. Now, of course, if you go back 20 years and find your old Radeon GPU sitting in a drawer, it probably won't support that. But the new ones it supports. So ROCm is a very full-featured open source stack, really designed to work in the same ways as the CUDA software stack. And of course, as I said, the real strength of ROCm is its open source. So you can go out and you can get the source for it. You can make contributions. You can go and compile it. You can do whatever you want with it because it's all open source. And I have a very hard to read figure over here, but you can see there's a lot of different components to it. One component to it is the HIP environment, which is a lot of the runtime and kernel extensions. So that includes some of the compilers. Now there's a whole bunch of different tools. So when I say this is one of the components, this is one of the components. There's a lot of different tools that I'm not mentioning, but HIP is one of the bigger tools. There's the HIP-CC, which is a front end to C++ and Perl. FLang, there's actually a Fortran front end as well. Hipify, which can convert CUDA to ROCm, and of course your make CMake as well for building your applications and in a debugger. And there's also recently added some profiling tools as well. These are the ROCm libraries. I won't go through them, though I do think the ROCm names are a little bit cooler than the other side. But it's a very full-featured set of libraries there. The development has been continuous since 2016. In 2016, the first version 1.0 was released, and that was really focused on HPC. In 2019, 3.0 was released, and that was more focused on AI. And then subsequent generations have been released to support different GPU models. In 2022, 5.0 was released to support MI200, and in 2024, the full support for the MI300 was released in version 6.2. I'm sorry, 6.1. 6.2 is the current release, and that added some additional profiling tools so you can see what's going on while you're running your code. Some references, like I said, it's completely open source, so if you want to go out and take a look at this, we've got a whole set of documentation. There's a GitHub where you can go get the source files, and there's also a community where you can ask questions and share experiences with other users. That's what I have.
Okay, so let's talk about the opportunity for data processing unit in AI. Okay, so to motivate this, right, one kind of known trend is that the traditional, server architecture that is more CPU-centric has been getting more and more burden in the recent past, right? And that's because the increased complexity, not only software and hardware, and there's this terminology called data center tax that's been introduced since, I guess, 10 years ago, ISCA 2015. But basically the idea is that, as we go through cloudification and everything like that, right, there's more and more infrastructure stuff being done, and these are data-oriented related stuff. And then this could include, virtual machine, managing virtual machine, dealing with disaggregated resources, right, like for storage, there's NVMe over Fabric. And then on the hardware side, right, the server these days, there's more and more devices that is in the server. Right, and this would be higher speed NIC, smart NIC, DPU, and all that, right? The data power compute type of accelerator, like GPU, right, or AI computer or NPU. There is also better and better disk, right? So the speed and feed of these devices are improving rapidly, and CPU getting more and more burden. So there's many data out there, and I'm just quoting what I thought more notable one, which is a study by Google and Facebook. It's a 2015 paper in S+ 2020. right? This is kind of they're studying the fleet of servers they have and showing that really these data center attacks of running infrastructure functions, are real, right? And it looks like over time the burden has increased. So, what's happening in the market is that the so-called data processing unit, or DPU, right, has been proposed so that we can, offload and accelerate these infrastructure data processing oriented tasks, right, from the CPU to the so-called DPU, right? And then a cartoon here, obviously, but the DPU will handle all the different infrastructure functions, virtualization, networking, storage, and so on and so forth. And the intent is, if you do the DPU properly, then obviously you can improve efficiency because you free up CPU, and you can also better keep up with the improving speed and feeds of the devices, right? And by the way, obviously, DPU is a kind of marketing term. Some other people call IPU, infrastructure processing unit, right? SmartNIC, super SmartNIC, and so on. But in this talk, basically, what I'm talking about DPU is anything that is used to, offload and accelerate the infrastructure data processing task. And there are multiple DPU products already entering the market, right? And then I guess a typical analogy I would give to people in the old days, we have a general purpose CPU that does everything, right? And then at some point, graphics becoming more popular, and it occupy a lot of CPU, and then then GPU was made, right? And obviously, for AI, it also turns out to be you can add AI compute in there, so that becomes more mainstream, right? And similarly, for DPU with infrastructure and IO processing, more and more, people are looking at offloading this, right? And there's multiple, offerings out there, right, including from MangoBoost. And notable approaches for this DPU are, it could be FPGA-based or ASIC-based, but usually the card has some number of CPU in the card, so you can run software, you can run full infrastructure software there. And there's some form of hardware acceleration in the card as well that's assisting the CPU, right? And there's multiple FPGA and ASIC-based options. For MangoBoost, we focus on DPU solutions, so we have more hardware acceleration IP that we can put on FPGA. We can compose them together. We can even harden it on chiplet or SoC. But for now, we focus on putting it on FPGA. And in fact, what we're showing in the case study is our solution on top of AMD FPGA. Okay, so now let's talk about opportunities for DPU and AI systems. Obviously, AI system is very complicated, so it's kind of like a bit high-level cartoon picture to kind of get the point across, right? But basically, the typical setup is there's a fleet of GPU servers, right? Not shown in there, but inside a GPU server box picture, there's also multiple GPUs in there. So 8 GPUs in a server, for example, becoming more common. And then there is sort of networks that go across, right? There is sort of the inter-GPU network or network across a different GPU server. These are for things like collective communication, for the communicating data across GPU, from one GPU to another across servers. And there's also a GPU to a GPU communication that is intranode or within a server, and this would be using peer-to-peer communication or GPU to GPU fabric, things like that. And finally, there's also the access to outside, right, to get storage, and that would be a storage network, right? And so the inter-GPU network, people could use RDMA, Rocky V2, InfiniBand, and so on, is again collective communication type. And for within the node, it could be peer-to-peer communication. And for storage network, it could be NVMe over Fabric, either over Rocky or over TCP, right? And the point here is that, as you can see, there's all the orange part, right? There's a lot of places where DPU can help, right? Because whatever data move, right, in and out, going through the network and from the storage to the GPUs, right, and then a GPU to another, then they can potentially get help from the DPU in there as data move, improve and the processing of the data. Okay, and then for this upcoming case study, right, that I'm going to talk about next, we're going to focus on storage, right? So this will showcase how DPU can help in both NVMe over Fabric, especially over TCP, as well as the peer communication, so you can directly put data on the GPU bypassing the CPU. So we're not going to cover the inter-GPU network, although we do have solution both for RDMA, inter-GPU, and then storage as well as inference. But the focus today is for the storage. So let's talk about the case study. So here, we're targeting a LM training case study with DPU accelerated storage. And for that, let me introduce our solution, MangoBoost GPU Storage Boost, as well as the baseline system, right? So let me start with the baseline system. So the baseline here is shown there, right? Essentially, we can have a normal NIC. We use Connect X in this case, and then we can run software, and we want to run essentially NVMe over TCP, to access the target storage server at the bottom there, depicted at the bottom. And in this case, one of the possible challenge will be, we have to run a bunch of software on the CPU, right? Obviously, we need the ROCm because we need the ROCm to access the AMD GPU. But for NVMe TCP, right? Linux have standard NVMe TCP stack. You can run it, and that's what we use for our baseline. But for that, we run NVMe TCP and the TCP, and then the driver, right? And in this case, the host see the device as an NVMe TCP device. And moreover, the data also have to go through the bounce buffer in the host memory and then go to the GPU. So that's kind of the baseline. So there's two kind of red dots there we're highlighting. And the first part of our solution is this NVMe TCP full hardware acceleration. Okay, so in this case, the picture is shown illustrated on the next of the baseline, right? Here, if we once we put the NVMe TCP hardware acceleration on DPU, what we do is that all the NVMe TCP software stack got hardened and moved into the hardware. And also, the hardware have some CPU for the control software. So what we can do is the DPU is seen as the host CPU as a local NVMe device. So you see as an NVMe PCIe device there. And then what I used to run on the CPU host now goes to the DPU. And if we go a bit closer inside the DPU, here in our solution that we're showing, we have a FPGA and embedded ARM CPU core. So what we want to highlight here is we actually accelerate everything, all the hardware data path, and for the full NVMe TCP, including stateful TCP under the hood, on the FPGA. So this is different than running it on the ARM core on the CPU, right? The ARM core on the CPU is really for control and for lightweight software stuff, right? There's PDK and DPU driver. So that's kind of how we first achieve the improved efficiency, and we'll show the results, in a bit. And the second part, right? Even the solution that we have before is not yet complete because we still need to move the data from the DPU to the GPU, right? If you don't do anything, it will show almost, on my right there, it will show basically the data have to go to the host memory first, bound buffer, right? And then go to the GPU. But here, what we add on top of our previous solution to complete the GPU storage boost is the peer-to-peer communication. So DPU will receive the data, and then it go peer-to-peer to the GPU bypassing the CPU. So with this, right, we can have truly more efficient data flow. And then next, let me talk a bit about the software enabling, right, just to kind of get a sense of how we make this work. Basically, a lot of user applications typically access the data through the file POSIX API, right? So, and then the baseline on my right, right, further right, it shows basically a POSIX file go to standard NVMe TCP Linux stack software, right? And in our case here, what we do is we make a what we call a Mango file, and I'll talk a bit more in the next slide. So this essentially have a similar set of API as the POSIX file, but it allows the buffer coming out to directly put stuff on the GPU instead of on the CPU. And it also obviously working out with our DPU in the back end. Okay, and then it's a bit detailed slide. I'm not going to go through all the detail, but I keep it there in case anybody interested. And obviously, you can feel free to talk to us offline or contact us. But what I want to highlight among some of this is that first, we essentially provide this, API, right? The kind of key API mentioned shown on the most right corner of my right, the orange boxes, right? First is just to kind of set up things, right? Set up the file, and then second is really to read and write file, right? And the bottom is to clean up, right? And then the code that we make is we make a Mango file kernel module, right? And then for that, the module we have to talk to the GPU side, right? For that, we basically have to modify and add an API to ROCm, so we can call ROCm. And and this is actually one of the things we like about ROCm because the open source nature. It's open source, so we basically just take ROCm open source and add our own API, and it can talk to our Mango kernel module. And then on the other side, on the NVMe side, right, we go over the standard virtual file system, and then the NVMe driver. We use the standard NVMe driver, just slightly modified, so that we can connect to our kernel module, right? And again, this is related to getting the GPU address and GPU buffer because we have to poke the data directly to the GPU, right? Instead of typically you go to the host CPU first. And that's it. So I guess the orange part highlights the part that we add or modify, but this thing works on top of the standard ROCm and as well as the Linux, NVMe TCP stack. Okay, so next, let me talk about the system testbed. The table kind of show a bit more detail. Again, I won't go line by line, but the main part is that basic, and shown in the figure, we have essentially populate our server with 4 AMD MI300X GPUs, right? And then we also put 4 DPUs. So basically the same testbed, but we use it for both baseline and the DPU-enabled one. In the baseline, we use standard Connect X6 NIC, right? And then DPU in the DPU one, we basically just take them out and we put our DPU solution there. Again, this is our solution on top of AMD U45N PJ card. And then we also configure it so that each DPU or NIC is in the same is assigned one-to-one to a GPU. Okay, so it's going under the same PCIe switch. That way, when you do peer-to-peer, you go to NIC or DPU, you just go directly to the GPU because one-to-one. You don't have to go all the way up to the other PCIe switch. And each of the NIC or DPU is equipped with 2 times 100 gig, so 200 gig per card. And because there's 4 cards in the system, so it's an aggregate of 800 gigabit per second of Ethernet coming out of the system. Okay, and then let's talk about the the evaluation. So we have 2 types of evaluation. We start with a micro benchmark, and then after this we'll show the workload with deep speed. So the micro benchmark, we just use popular FIO. Everybody knows FIO, right? And then basically to enable FIO, we do a little bit of setup in software here. The baseline, we couldn't find any ROCm that works with FIO out of the box, so we just make our own a little bit backend of the FIO. So we keep most of the FIO software intact. We just modify a little bit of the IO engines we add to it so that they can call the appropriate ROCm API to move data around, right? And that's what we call the libhip. That's our own creation that we add on the backend of FIO. And then for the DPU-enabled system, we have what called libgsb, similar approach. We keep FIO and just modify the backend IO engine so that it can talk to Mango file, right? And then from the Mango file, everything works with our DPU. So that's how we enable the FIO benchmark here. And then here is the results. So on the most right, on my right, I guess your left, there's the data movement bandwidth. So this is we measure the achieved bandwidth out of the storage system. And then we vary a little bit, if we vary on the x-axis, different block size, just to kind of see how things perform over different block sizes. And then on the y-axis, right, it's go up to 100 gigabyte per second, right, 800 gigabit per second, which is our aggregate network bandwidth. And then we have the line rate, dotted line, and then the 2 lines, right? The orange is from using DPU, right? Our MangoBoost GPU storage boost, and then the darker line is for the baseline, right? Using the standard NVMe TCP software, and you can see, essentially we got 1.7 to 2.6x higher bandwidth depending on the block size, and also notice that in the baseline, right, the CPU seems to get saturated after a certain block size, so it kind of plateau from that perspective. And again, this is the CPU is actually host CPU in the baseline runs the full NVMe TCP software. And then in terms of latency, in the middle part, right, the moving latency, we also show the latency improvement compared to baseline. Again, because we're not having the data go to host memory and then go to GPU, right? There's no bounce buffer. We go direct using peer-to-peer. So in that case, we got 25% lower latency on average. And then finally, on my left, you're right, the CPU core use, right? And again, here the CPU basically needs to run some threads for the FIO itself, for the application. So that one we cannot get rid of because you have to run FIO. And then in the baseline, in addition to that, it also runs NVMe TCP. But in the DPU case, all the NVMe TCP is handled by the DPU. So we save a lot of cores, like up to 36 cores, 22 to 36. And basically, mostly we free up all the CPU that's used for NVMe TCP software. Obviously, there's remaining 16 cores also. That's for the FIO stuff. And then a little bit for the NVMe PCIe driver, because the host still see the DPU card as a local NVMe PCIe, right? Okay, and then for the next evaluation, beyond micro benchmarking, right, we actually also evaluate a workload. And this is the Microsoft DeepSpeed we talked about it during the introduction. Right, and here the setup is we use Llama 3.1, as the model. Right, this is a very well-known latest model from Meta, and then we also essentially have to modify a little bit on the back end. So similar approach to the FIO. We only modify the back end part of the DeepSpeed. So everything else is not touch, standard, right? And then there's a swapper module, which is the backend that handle the data movement when you spill data from the AI states from the GPU memory to storage, and we modify that so you can call Mango file, right? And that's how we get it to work with our solution. And essentially, we compare again head to head. The only difference is just the NIC versus DPU. Okay, and then the result is shown here. So we showed the same type of metrics as the micro benchmark. The latency one in the middle basically is not that easy to get the latency because now there is also the DeepSpeed workload itself running as well as the latency of accessing storage. So it was not easy to distinguish it. But we have data movement bandwidth still reported and CPU cores used. And as you can see, basically the improvement is quite noticeable. And this is kind of within the range of what we saw with micro benchmark FIO, but on the lower range because obviously the DeepSpeed itself have to run stuff, right, in terms of just the FIO. So we're on the lower range of the FIO benchmark that we saw, but still quite significant, right, 1.7 and then saving 25 cores. And I guess one other note, to show that the solution is general. I mean, we work with ROCm, right? So ROCm support multiple AMD GPU. So we also have AMD MI210 GPUs. So we're not reporting it here, but if anybody interested, you can contact us for detail. But we run similar set of experiment with MI210. And then we also show similar kind of type of improvements as well, as expected. So, not here, but we can talk about the result if anybody is interested. Okay, so to sum up, right, efficient storage system is becoming really a key factor in AI system, and this is because there's a lot of compute already, right? We need to feed the beast in a way, bring data to the compute, and the model is so big that and including the other states, right? There's optimizer states, not just the model. It doesn't fit in the GPU device memory anymore, so you have to spill. Right, and that where smarter storage subsystem it really is critical. Obviously, Craig has go over the AMD GPU ecosystem, which is quite state of the art, and then we also talk about DPU and how it can improve, storage system efficiency and infrastructure in general. Right? In particular, we highlighted one of our solution, which is the GPU storage boost from MangoBoost, and then our case study. We have concrete numbers, and we show improvement in both storage throughput, as well as a reduction in number of CPU that got freed up, right? Because things are accelerated, fully in the DPU. And last but not least, if anybody interested, contact us, contact at MangoBoost.io, and we can provide a demo. With that said, quick disclaimer, thank everyone for staying and open for question. So I guess the pricing, I have to repeat the question. What is the pricing of the MangoBoost solution? So I would say the pricing is competitive, and you might have an impression that FPGA pricing is super high, but if you talk to us in detail, and then we have partnered with AMD also, you might be surprised that it's actually quite lower than you think. So it's competitive.
Competitive to Mellanox?
Competitive to other offerings. Again, I can talk the detail offline, but maybe not in the public forum. It's competitive, yeah. Sir.
You had a picture where you had a combination of ConnectX and your DPU. What's the ratio of how many ConnectX and how many DPUs you're using in that?
You mean in our setup?
Yeah.
Let me see. So basically, the intent is the same number because the intent is the baseline does not use DPU, right? It has 4 network cards, and we use 4 ConnectX. And we simply replace 1-to-1, right? Instead of using a ConnectX, let's just put a DPU. That's right. That's it. So it's the same. Yes, sir.
These are impressive bandwidth numbers.
we have the 2 by 100 gig per card, and then there's basically 4 of them in the server.
Going back to slide 29.
So 29.
28 then. It says gigabytes per second. How do you transport 80 gigabytes per second over a 100 gig network?
So I think I'll make it clarify. I guess the question was, I forgot to repeat the question, sorry. So the question is, what was the network setup? And then, to explain that result. So basically, it's 800 gigabit per second aggregate. And then, so I just converted to byte. So that number is 100 gigabyte. Yes. So the top line is basically 800 gigabit or 100 gigabyte. And we're close, but, it's not 100%. Obviously, you can't get 100%. So for the red line, no connect X is just our DPU, and then for the baseline, we use the we use the connect X6, and then but the NVMe TCP stack is run in software because connect X doesn't have NVMe TCP acceleration.
Buy something from Mellanox which runs on their card.
The Mellanox doesn't have NVMe TCP acceleration.
Okay.
Yeah. So. By the way, we also have RDMA, but we thought the NVMe TCP is more unique. So obviously, RDMA will be more standard. So you get a point. If you use RDMA, there's an RDMA hardware. But there's the TCP, there's no hardware. Yes, sir.
Are you going to submit your driver to Linux like in Grandbit?
You mean the driver we have here? I guess. Yeah, obviously we want other people to use it. I think the specific plan we're still finalizing it. But if nothing else, if you contact us and have interest, we can talk and make it available. But the intent is for us to enable other people to use it. So that's kind of the plan. Repeat the question is: are we going to contribute to Linux? So the driver to Linux. That was the question. Sorry. Yeah, so the Mango file, I think. So the Mango file is basically the software library we make so that it can work with our DPU and enable the peer-to-peer. So it's in a way it's tailored to our DPU, but the intent is to create a file abstraction, right? Similar to POSIX, but this is allowing the peer-to-peer communication. So the target buffer, instead of CPU, it will go to the GPU memory. And I guess one other thing is if anybody interested in talking more detail, actually from MangoBoost, we have 2 of our lead engineers here, Hitek and Changsu, somewhere here, that would be happy to talk to you guys more in detail for this low-level stuff. Yes, sir. In this case, we're not using IPsec, but we have different IP. I think we have security IP as well. Okay. So the question is, do we also support IPsec? I guess one other question is the answer is that so we use FPGA right as our deployment. So any hardware IP, technically speaking, we can offload there. So we have different mix of IP. Obviously, for this talk, we're not focusing on IPsec, but contact us and we can mention we have security IP as well that we can put in there, and we can compose different IP together. In this case, we showcase our full TCP accelerator, NVMe IP, right, and peer-to-peer IP combined together to make this solution. And we can mix other things and put it on top of FPGA. And we also have a software layer on top, so just like what I showed here, to make it so that it's seamless to deploy. Right? People doesn't have to know there is an FPGA in it, easy to deploy. So it's easy to deploy as other NIC card, right? It's hiding under the same standard kind of driver type of thing.
How big is your FPGA?
So we can support multiple options from the known FPGA vendors that's data center ready. Right? There's different scale. For this one, we use U45N from AMD. You can look at the spec, but we can go up higher, you can go smaller, and we usually look at the use case, and we obviously don't want to be overkill, so we can go with small FPGA. But so we have tools, and basically our secret sauce is hardware generator, set of IP and tool, so we can go up, go down. We can even chipletize things and harden things in SOC if people want that. Yeah. Okay, if there is nothing else, again, thank you very much, everybody, for staying until the end.